Hi everyone. In this video, I'm going to illustrate how to use the L'Hopital's rule when we compute limits for a specific type. So let's talk about the indeterminate powers. So often if you try to take a limit and if you get, let's say, 0 to the 0 power, that's one of the indeterminate power. Or if you get, let's say, infinity to the 0 power, that's also an indeterminate power. And last one, if you have 1 to infinity, that's also known as the indeterminate powers. So these are the three indeterminate powers we have. If you encounter any of these, you would have to use L'Hopital's rule. So let me illustrate how that method works. So here's the example we're going to be working on. So say you want to find this limit. Limit as x approaches positive infinity of the function 1 plus 2x to the power 1 over 2 ln of x. So if you try to approach, as x goes to infinity, what happens? Well, this limit, it looks like, so 1 plus 2 times x is getting very large, so it's going to be infinity. And then if you try to reach infinity, as x goes to infinity, the exponent will be 1 over 2 times ln of infinity is also infinity. So you got 1 over a very large number, which is 0. So that's the indeterminate power. So this is what we call indeterminate power form. So since we get that, now we can apply L'Hopital's rule. So before we apply L'Hopital's rule, we're going to rewrite the function in the following form. So you're going to let f of x be equal to the function that you're taking limit of, which is 1 plus 2x to the power 1 over 2 ln of x. So you're just going to let this to be your function f of x, because that is the function you're taking limit of. So once we do that, we're going to apply logarithm to both sides, because if you have an exponent that is a function, you want to pull it down, make it into a product. And the function that does that will be logarithms. So we're going to go ahead and take logarithm on both sides. So if you do that, you will have ln of this function f of x is equal to ln of 1 plus 2x to the power 1 over 2 ln of x. Now, because we apply ln, now we can bring this exponent forward, make it into a product. So our ln of f of x is simply 1 over 2 ln of x times ln of 1 plus 2x. Or if you want, you can just write it as a quotient, ln of 1 plus 2x over 2 ln of x. So that's what we're going to replace with our limit. So take a look at what the limit becomes. So we have rewritten the function using ln. So we're taking the limit as x approaches infinity of the function f of x, and we apply ln to f of x. So that means I can write this as the limit as x approaches infinity of ln of f of x. So that will be ln of f of x. And then I'm just going to go ahead and plug this in there because that's what my function is equal to. So this is equal to ln limit as x approaches infinity of ln of 1 plus 2x over 2 ln of x. So we do that so that it's easier to work with. And at the end, of course, we'll modify that. So now let's apply the limit. If you take the limit, well, what will this limit tend to? On top, you're going to get ln of 1 plus very large number. So let's say infinity. And on the bottom, again, 2 times ln of very large number will also be infinity. So this is an indeterminate form. Once it is an indeterminate form, now by L'Hopital's rule, you can do the following. So here we're going to apply L'Hopital's rule. So this is the indication. L'Hopital's rule tells us to differentiate the top and differentiate the bottom. So think about this is your top. We're going to take the derivative, and then we're going to take the derivative here. So we're going to go ahead, and this is going to be the limit as x approaches infinity. We're going to take the derivative of the top, which is ln of 1 plus 2x, and then we're going to take the derivative of the bottom, 2 ln of x. I'm showing the steps, but that's what we're going to do right now. So this is equal to the limit as x approaches infinity when you take the derivative of ln of any function, it's 1 over that function times the derivative of the inside, which is 2 in this case, using chain rule. And on the bottom, you have 2, derivative of ln of x is just 1 over x. Now let's go ahead and simplify before we take the limit again. So you have the limit as x approaches infinity. We have 2 over 1 plus 2x times x over 2. So I reciprocated the bottom fraction. And this is equal to, we're still just rewriting limit as x goes to infinity. So here we can cancel these out. Then we're left with x over 1 plus 2x. Now, if you take the limit, this limit will give you, so as x goes to infinity, you compare the degrees of the top and the bottom, they're equal. So here, this has a degree 1, this has a degree 1. So the limit of this is the coefficient in front of them, which is 1 over 2. So this limit is 2. Sorry, this limit is 1/2. So now, what did we do earlier? Well, we had to rewrite the function because we couldn't just take the limit right away. We introduced ln into the function. So what we have was so initially we were looking at the limit as x goes to infinity of 1 plus 2x to the power 1 over 2 ln of x. And we rewrote in terms of ln. So this was actually, if you were to rewrite, this is the limit as x approaches infinity of ln of f of x. But since you applied ln, you can just do that to a problem where you have to exponentiate as well. So therefore, you can also write the equivalent statement. Instead of writing it this way, we can also say this is equal to e to the ln, the limit as x approaches infinity of ln of that function f of x. Now that is fine because both of these functions are nice and continuous. And now we know the limit, what that limit happened to be. That was 1/2. So our final answer is actually e to the power 1/2. Or you can just say this is square root of e. So any of this is fine. So if you apply ln, you must also apply exponential at the same time because the rewriting has to make sense. So the limit of this function is e to the 1/2.